Hello students, as discussed in the last video, today we'll talk about cosets. So without wasting much time, let's learn what is a coset. If G is a group and H is a subset of G, then we denote the set AH where H belongs to H and A belongs to G. Now, what do we call this set? We write it as AH. Alright? And when we write capital H on the left hand side, it means this is okay. So, why do we define these differently? Because these operations need not be commutative. Okay. So, if G is a group and H is a subset of G, then we denote this set by AH. This is a symbolization, and HA as H into A, where H belongs to capital H. Now, when H is a subgroup of G, now when H is a subgroup of G, we say that AH is a left coset of H in G. Okay? We say that AH is a left coset of H in G containing A. We will prove this how A will always belongs to AH. And similarly, HA is a right coset of H in G. Again, it contains A. We will prove that these cosets contain the element. Now, what is special about A? A is called coset representative. Alright. So, if G is a group, H is any subset of G, we denote AH as A into small h, where H is any element of H. Similarly, we define HA. Now, when H is a subgroup of G, then we say that AH is a left coset of H in G containing A, and we will prove that this contains A. Okay, similarly, HA is a right coset of H in G containing A. Okay, so let's take some examples of cosets. Okay. Now let G is S3. We know that S3 is symmetric group of degree 3 and H is this collection of permutations. Okay, so let's calculate 1 2. Now 1 2 is an element of G. 1 2 into H. Okay, so this will contain elements 1 2 into 1 and 1 2 into 1 3. Now what is its value? 1 goes to 3, 3 is fixed, and similarly 3 goes to 1 and 1 goes to 2. Similarly, we calculate 1 3 into H. What is its value? 1 3 into 1 and 1 3 into 1 3. This is equal to 1 3 and square is identity. Okay. So similarly, we can calculate all other values, all other cosets of this subgroup. Okay. Next, we shall do some properties of cosets. All right. Okay. So first property is, as we wrote in the definition itself, that AH is called the coset representative, A is called the coset representative and AH is a left coset of H in G containing A. So very first property is A belongs to AH. Here the assumption is that H is a subgroup of G and A, B belong to G. A and B are any two random elements of G. Okay. So very first property is A belongs to AH. Okay. Since H is a subgroup of G, this implies E belongs to H. Now the identity of H and the identity of G is same because identity is unique. Okay. So A can be written as A into E and E belongs to H. So there exists B belongings to H such that, or H belonging to H, where H is E, such that A is equals to A into H. Okay. So therefore A belongs to AH. Okay. Second property is AH is equals to H if and only if A belongs to H. Okay. So let AH is equals to H to prove A belongs to H. Okay. Since E belongs to H, this implies A into E belongs to AH. This implies A belongs to AH. This implies A belongs to H because AH is equals to H. Alright. Now secondly, and conversely, we shall prove if A belongs to H, we shall prove that AH is equals to H. Okay. So let X belongs to AH. This implies there exists there exists B belonging to H, or say H belonging to H, such that X is equals to AH. Okay. So now A belongs to H, H belongs to H. Since H is a subgroup, therefore AH belongs to H. This implies X belongs to H. Okay. So for every element that lies in AH, it belongs to H. Therefore, AH is a subset of H. Okay. So conversely, if X belongs to H, okay, if X belongs to H, we can write X is equals to A into A inverse H. Okay. X belongs to H. We can write X is equals to this. Now we can write A inverse because A is invertible. Because G is a group. Okay, since A is invertible. By associativity, we can write it as this. Okay. So we are already given that A belongs to H. Okay. So A inverse will also belong to H. A inverse X will belong to H. This implies X is equals to A into A inverse X belongs to AH. This implies H is a subset of AH. Now from 1 and 2, AH is a subset of H and H is a subset of AH. Therefore, AH is equals to H. Okay. So the second property was that AH is equals to H if and only if A belongs to H. So let's revise its proof. Now, if AH is equals to H, we need to prove that A belongs to H. Okay. Since E belongs to H, okay, since H is a subgroup of G, this implies A into E belongs to AH. This implies A belongs to AH. This implies A belongs to H because AH is equals to H. Now, if A belongs to H, now we need to prove that AH is equals to capital H. Okay. Now, if X belongs to AH, okay, so this implies there exists some H belonging to H such that X is equals to AH. Now, H belongs to H. Therefore, A belongs to H. Therefore, X belongs to H. Similarly, if there is some element in H, we can write it as A inverse into X. Now, X belongs to H, okay? A also belongs to H. Therefore, A inverse belongs to H and hence H is equals to AH. Okay? Now, third property is very interesting. AH is equals to BH or AH intersection BH is 5. Okay. So what does this property say? This property says that any two cosets or any two left or right cosets of H in G, either they are distinct, either they are disjoint, or they are equal. Either they do not have any element in common, okay, or if they have any element in common, that means they are equal. Okay. So to prove this, we shall assume let AH intersection BH is not equal to 5. Okay. Now we shall prove that AH is equals to BH. Okay. Now since AH intersection BH is not equal to 5, this implies there exists some H, X belonging to AH and X belonging to BH. Now X is equal to AH1 and X is equals to BH2 for some H1, H2 belonging to capital H. Okay. Now to prove AH okay, this is to be proved. Now H is a subgroup of G and X is equals to AH. So A is XH1 inverse and B is XH2 inverse. Okay. Now whether X belongs to AH or it belongs to BH, it is inside the group G and it has an inverse. Now we don't know where the inverse lies, whether it lies inside H or outside H. We are not concerned about that. Okay. But we know that inverses of H1 and H2 will lie inside H. Okay. So now let X belongs to AH, or say consider any element of AH. Okay. This can be written as XH inverse, XH1 inverse. Okay. This can be written as what was X? X is BH2. Now since H is a subgroup of G, therefore H2, H1 inverse belongs to H and hence this belongs to BH. Therefore, AH is a subset of BH. Similarly, consider any element BH of B capital H. This can be written as, write B as H2 inverse. Okay. Now X can be written as BH2. Sorry, we have to write X in the form of A. X is a multiple of A. So we can write it as AH1. H2 inverse Now since H1, H2 belong to H and H is a subgroup of G, H1, H2 inverse will lie in H. Therefore, this belongs to AH. This implies BH is a subset of AH. So by 1 and 2, we have AH is equals to BH. So this is a very interesting property. So whenever any two left cosets of a subgroup are there, we can conclude that either they will be disjoint or they will be equal. If at all there is any, if you are given that there is any element common between the two left cosets of a subgroup or of a group, that means they are exactly equal. So this is a very interesting property, and we have completed the proof of this property. We assumed that if at all this intersection is not equal to empty, this will be equal. These sets will be equal. Okay. So AH intersection BH is not equal to phi. Hence there exists some element that belongs to both of these sets. X belongs to AH and X belongs to BH. So X is equals to AH1 and X is equals to BH2 for some H1 and H2 belonging to H. Okay. So now, since we do not have to worry about existence of inverses in a group, so we can write A is equals to XH1 inverse and B is equals to XH2 inverse. Rather, H is also a subgroup of G. Let AH belongs to this subset, okay, AH. Now we need to prove that this is a subset and converse. AH is equals to XH inverse. Now X can be written as BH2, okay. From here we can write X as BH2 into H1 inverse, B H2 H1 inverse. Now this belongs to H because this complete H is a subgroup, and hence H2 H1 inverse will belong to H, and therefore this belongs to BH. And similarly we can prove the other side. BH belongs to is equal to H2 inverse. X can be written as AH1. We need to write it as a multiple of A. AH1 H2 inverse is equals to A H1 H2 inverse. Because H is a subgroup, it belongs to AH, and hence BH is a subset of AH. From 1 and 2 we get AH is equals to BH. Okay. So this was third property. Next we come to the fourth property. So in the second property, remember, second property was that AH is equals to H if and only if A belongs to H. Remember this property to prove this. Okay. So multiply left hand side by A inverse. Okay. So H is equals to A inverse B H. Okay. So rather this implies A inverse B belongs to H, and instead of this we can apply double implies also. Okay. So we can go back to this. Now because conversely if A inverse B belongs to H, this into this will belong to H. Okay. Therefore A inverse BH is equals to H, and hence AH is equals to BH. So this was the fourth property. And fifth property is that the order of any two distinct left cosets of H and G is equal. Now to prove this property, we just need to define a mapping from AH to BH. Now what is the variable in this mapping? An element of H. Okay. So phi actual A and B are constants. Okay, so and the domain will be the elements of AH, but actual variable will be H. Is still a constant in this. Okay, so phi of AH is equals to BH. Now to prove that, sorry, small h belongs to H. Now once we prove that this is 1 1 onto, our proof is done. Clearly this is onto, because for any element belonging to BH we have an element in AH. Okay, we can write phi of AH is equals to BH. So that's not a problem. Phi is onto, there's no need to prove. Now to prove that this is 1 1, let phi x1 is equals to phi x2. Now what are x1 and x2? x1 and x2 belong to AH. This implies x1 is equals to AH1 for some h1 belonging to H, and x2 is equals to AH2 for some h2 belonging to capital H. Okay, so phi of AH1 is equals to phi of AH2. Okay, this implies this is BH1 is equals to BH2. Now left cancellation laws hold in a group, so we can cancel B. This implies H1 is equals to H2. This implies AH1 is equals to AH2. Left multiply by A on both sides. This implies X1 is equals to X2. Okay. You can say that here left cancellation law, or you can multiply by inverse of left multiply by inverse of B. Uniqueness of inverse holds, so therefore we can cancel these. So we have proved that this is a 1 1 onto mapping, and clearly this is a function. To prove that this is a function, we need to prove this thing backward. X1 is equals to X2, AH1 is equals to AH2. Again left cancellation law, left multiply by BH1 and similar. So this is, this can be traversed from top to bottom and from bottom to top, and you will be able to prove 1 1 and it is a function. Okay, so onto we have already proved. Since this is a 1 1 onto mapping from AH to BH, this implies their orders are equal. Okay. Now the sixth property is that AH is equals to HA if and only if H is equals to AHA inverse. Okay, left coset is equals to its right coset if and only if H is equals to AHA inverse. Now what is AHA inverse? This is equals to AHA inverse where H is any random element of the subgroup H. Okay, and A is still a constant for us, constant element for us. Now right multiply by A inverse. Okay, and similarly you can left multiply or right multiply by A inverse. So there's nothing to prove in this. Now last property is, we already know that H is a subgroup of G, so we would be interested in knowing whether AH is a subgroup of G or not. Okay, so multiplying any element A with the elements of a subgroup, it doesn't necessarily lead to the subgroup of to a subgroup of G. Okay, now we know that A belongs to AH. Okay. Now we are multiplying. Now maybe I don't know how many elements are there in H. They can be finite, they can be infinite. Okay. So for every element in H, we have an element in AH. Okay. So order of AH is at least order of H. Okay. Rather, this will, we have already proved in fifth property that AH is equals to BH. If you take B as identity, then this becomes H. Order of H will be exactly equal to AH. Now we are interested in knowing the condition when AH becomes a subgroup of G. In all the properties, we generally have had the condition that if A belongs to H, we have, we satisfy that property. So here also we have the condition if and only if A belongs to H. Okay. So now, clearly if AH is a subgroup, this implies identity belongs to AH. Okay. So if AH is a subgroup of G, we need to prove that A belongs to capital H. Alright? Because right multiply by H, right multiply by any element of H. Okay? What will be EH? If E belongs to AH, okay? So this implies H is equals to AH. Now this is equal if and only if A belongs to H. So conversely, we prove that for now we have proved that A belongs to H. If A belongs to H, this implies AH is equals to H. Now we know that H is a subgroup of G, therefore AH is a subgroup of G. Okay. So our last property was AH is a subgroup of G if and only if A belongs to H. Now today in this video we have talked about cosets. What is a coset and what is the definition of a coset, what are properties of cosets. We also saw one example depicting how cosets are calculated. In the next video we will talk about Lagrange's theorem, which makes use of the concept of cosets. And not only the Lagrange's theorem, going ahead we'll use these cosets in various theorems to prove various results. So stay tuned and keep watching these videos. Thank you.